Hello, my name's Mr. Maguire and welcome to this presentation on forces. This lesson follows a previous lesson looking at forces and elasticity, and today we continue to look at Hooke's law, but we are looking at a required practical using that knowledge base. So this is lesson 5 and 6 that are combined together. So before we start, let's find somewhere quiet to work, free from distractions as possible, and you will need a pen and paper. If you have any graph paper at home, that would be helpful, and if you have a calculator, that would also be helpful. So on the top of your piece of paper, I would like you to put down the title that's written there, Hooke's Law and required practical. You've got 60 seconds to get yourself settled. Thank you. Let's have a look for a moment then at the life and times of Robert Hooke. In 2003, it was 300 years since he had died, and yet because of circumstances in his life, we don't remember in the same way as we remember peers who were around at the time who were far more famous, such as Isaac Newton. He was a surveyor, and because of that became very wealthy in redesigning and helping to replan London after the Great Fire of London in 1666. But he has many great discoveries named after him in physics and biology, and it's because of him that you would use the word cell in looking down a microscope. He died poor and relatively unknown, and also had no immediate family, so therefore his name did not carry forward into the future, and as a result we don't know him in the same way as we now know Isaac Newton. So let's look at our challenge for today, to be able to safely investigate the effects of applying a force to a spring, and aspire to be able to accurately analyze your data using a graph to measure the stiffness of your spring. So this is an image that you should recognize from the previous presentation on Hooke's law. I'd like you to recall as our starter what the relationship is between the mass and the extension. I'll give you 30 seconds to think about that. Okay, so this image that's in front of us here, first of all we have an unextended spring, then we have a mass on the spring which extends that spring. We double the mass, the extension is doubled. So that relationship, as we should remember from the previous presentation, is directly proportional. What that would look like on a graph is a straight line. The important point being that it's not just a straight line, it's a straight line that comes from the origin. So if there is no mass, there is no extension. And we're going to be using that knowledge again as we learn how to produce those graphs. As this is a required practical, you need to be able to explain the equipment that we use and how it is set up. So on the slide in front of you, first of all, we have a list of equipment, including the spring that we will be testing, a meter ruler, then we've got a stack of weights. It's 1 kilogram, which is 10 newtons, and we'll look at that in a moment. We've got a clamp stand, we've got 2 clamps and bosses to enable us to hold the spring and to support the ruler. And then we have a suitable pointer, for example, a splint and a piece of tape. I've used a cocktail stick in the clip that you will watch. So I'm now going to put that on, and you afterwards will then be given the list of equipment, and at that point then you need to immediately start free writing what it is that the experiment looks like and how it's set up. That should include a diagram that will help you in reducing the length of your explanation. So you watch the clip now. This is the equipment for the required practical on Hooke's law, extension of an elastic substance. So we have here a clamp stand and boss, and we've got a G-clamp holding it firmly to the desk. That's attached to a ruler, 1 meter ruler. Then we have the spring at the top there with a marker on it that we can read against. You can see that the unextended spring is 2 centimeters in length, and we're going to be hanging selected weights from that as we go through the practical. Let's just have a look for a second at the other equipment. We've got some more slotted masses to hang on to the spring, and looking at the maths for a second. From previous lessons, you know that the weight equals mass times gravitational field strength here. Mass being measured in kilograms, and G, or gravitational field strength, is 10 newtons per kilogram. I have got a 1 kilogram set of masses here today. So 1 kilogram times 10 newtons per kilogram is giving me then a weight of 10 newtons. And what that means is that the 100 gram slotted addition is 1/10 of a kilogram, which means that it is weighing 1 newton. So I'm going to be taking selected pictures of those being added, and we'll be reading using the marker on the ruler as accurately as possible what the extension of the spring is. Okay, now you've watched the clip, let's write a list of equipment and explain how that equipment is set up, including a diagram. So we're now going to look at how we'll record our results. In a moment we're going to need to put a results table down, but I want to show you first of all how we will use the data to fill this in correctly. First of all, the first slotted mass that we add to our practical equipment will be 100 grams. But obviously in the header of the mass column it says in kilograms, so we need to divide that by 1,000. And that gives us then a mass of 0.1 kilograms converted. The next column says newtons, and we need to convert our 0.1 kilograms into newtons. From a previous presentation that you have learnt, we should know that weight equals the mass, 0.1 kilograms times gravitational field strength, which we will take as 10. So we're going to take our 0.1 kilograms, multiply it by 10, and that will give us an answer at the weight being a 1 newton. Now we need to use the ruler and the data that we collect And as an example, we have here that from the ruler we could see it was 4 centimeters length that we measured from the ruler, and that converted to meters divided by 100 is 0.04 meters. Now we need to be able to calculate the extension. In other words, we need to know how much the spring had a length of before we started the experiment. So we need to know the top line at this point. When the spring had no mass or weight, the length of the spring was 0.02 meters. So therefore, when we added the 1 Newton weight to it, we have to do this maths. We take 0.02 from 0.04 so that we know that the extension was 0.02 meters. That's just the extension. Now we can continue to add slotted masses and increase the number of newtons, and we will be going to 5 or 6 newtons. So here is a simplified version of the table with the calculations removed. And let's just add a little bit of detail and help for you so that you can get a good copy of this. You can see how the mass converts to weight. What I would like you to do now is to spend the next few minutes taking an accurate version of that table. I don't want to set a timer because it depends how accurately you can do it and how quickly. So pause the presentation now to allow you to do that. So now you've got a completed table, what I would like you to do is to concentrate on the length column. I'm going to show you now a series of images where you can clearly see how many slotted masses, 1 Newton weights, have been added, and you can see the pointer on the ruler. Try and read as accurately as you can the number of centimeters and millimeters, then convert that to meters and put it into the table. Each of those images will be up for about 20 seconds before they move on to the next image. So you'll need to be moderately quick in terms of recording the data for this piece of practical work. If you need to pause them, then do so as we run through. So that's our 1 Newton, looking at the ruler and taking down the measurement from the ruler. Moving to 2 Newtons, there's 2 slotted masses now. Again, look at the ruler and record down the measurement from the ruler. Now we're on 3 Newtons. Four Newtons now. Try and measure to the nearest millimetre if you can. 5 Newtons now. And finally 6 Newtons. So now we have collected some data and converted it appropriately and calculated extensions, we need to plot that on a graph. The question we're asking now is, which way do the variables go? When you're drawing a graph, it's important to remember that the x or across variable is always the independent variable, the one that is allowed to change. And in this case, the one that we changed and then recorded the results was the weight. So therefore, the y-axis or dependent variable is the extension that we are plotting. We're going to look at how to plot that graph correctly. It's important that we think about and talk about variables properly at this point. You need to ensure that your scales are correct and that your graph has a scale that fits at a reasonable size within the page, not squeezed up, and not one that doesn't fit properly on the page because it is so big. That makes it more accurate. So what I'd like you to do is to use your data, and I'd like you to draw your graph independently now using a pencil and ruler and put a line of best fit through it. Because it's directly proportional, that will need to be a straight line of best fit. Okay, so let's have a look at the data. I have taken this straight from the photographs rather than when I collected the images in the first place. So first of all, each one of these is the 1 Newton mass, 100 gram mass, weight I should say, that was added. So using the photographs, I've then recorded these particular lengths that the spring stretched to. First of all, when the spring had nothing on it, it was 2 centimeters long, which converted to meters is 0.02 meters. So looking at the photographs, I've then used the toothpick pointer, the fiducial marker as it's called, and I have taken these. Now I've gone basically 14.5 centimeters and then converted that to millimeters. So I've tried to go to the nearest millimeter in my results. So from that data, I've then subtracted my 2 centimeters from the original length of the spring before anything was added to it. I've subtracted that from each of them, and this is my data set now that I am going to plot as part of my graph. So my independent variable that I am allowing to change is my weight in newtons that will go on the x-axis, and my dependent data that I will plot will be the extension in meters that will go on my y-axis. Continuing for a second then, I've taken that data that you've just seen and I have gone up to 6 newtons here, 0 to 6 along the x-axis, and then on the y-axis I have gone up in 0.02 meters all the way up to 0.26 meters, which will allow me a good scale to plot my data on, to give me a good size of graph. So first of all, at 1 Newton, my result, for example, was 0.036. So I've gone to 1 Newton and gone up to 0.036 and put my cross. Now I know that it's directly proportional, so I have drawn a line of best fits going through the origin and getting as many points as close as possible to that line. And that's not a bad set of data. So have a look at your graph for a second. Does it have a title? If not, then please look at the names of your axis and how does X affect Y is a Very good way of writing titles. Have you put the units correctly next to your axis labels as well? Has it filled the page, or have you chosen a scale that's so small that it's not going to be very accurate? Are the points plotted accurately, and have you drawn a line of best fit neatly and accurately? Because this is a directly proportional graph, it should be a straight line that passes through the origin. So you've just seen the graph that I've drawn, and from that graph we are then calculating the spring constant. Looking at the equation that's in front of you now, the spring constant here is the K, F is the force, K is the spring constant, and E is the extension. So rearranging that equation for spring constant, and the spring constant equals the force divided by the extension. So if you now look at your graph and take from it a force and an extension and divide those points, you should end up with the spring constant in newtons per meter. Now, if you do that at any point going out from your axis to the line, you should end up with the same point because it's directly proportional and a straight line, up to the point where the graph shows that the spring no longer follows Hooke's law because it has passed its elastic limit. So let's have a quick run through the calculation of the elastic constant. First of all, elastic constant's equation, rearrange for K equals the force in newtons divided by the extension. I've taken a point on the graph, gone up at 3 newtons, which I've then inserted here, and the extension, which is 0.125 at that point. Just divided those two numbers, and I have come up with 24 newtons per meter as the calculation. Very straightforward. The thing that we should notice is that I should be able to then go up at any point on this and end up with a similar answer to that, because it's a line of best fit and it is directly proportional. So let's just remember that Hooke's law, F equals KE, or force equals spring constant times extension, and Hooke's law then stated the force is proportional to the extension up to its elastic limit. After this limit, the spring doesn't return to its original length. It is then permanently deformed. So in today's lesson, we have, for the challenge, been able to safely investigate the effects of applying a force to a spring. And then for the Aspire, we've been able to accurately analyze our data using a graph to measure the stiffness of your spring, and we have done that by measuring the spring constant K using the Hooke's law equation F equals KE. My name's Mr. McQuire. Thank you for staying with this presentation today, and goodbye.